And basically, the WESTalks series is brought to you by IC Impacts and UBC Future Waters. IC Impacts is the Pan-India Canada Research Center for Excellence, which serves as a new model for collaboration between the two countries. And they co-develop research in various fields such as infrastructure and water. And the UBC Future Water Group basically promotes a lot of interdisciplinary water research across the UBC campus. Just to plug this in, because this is a UBC student-led conference, the West Conference is happening this year. It didn't happen last year because of the pandemic, but this year we're back. It's going to be held on June 9 to 11. And Carl is going to be posting the link in the chat, and abstracts, our submission deadline is on April 15. So if you're interested in presenting or listening to some cool talks, please make sure you register or submit your abstract. This is the wonderful committee which has been organizing this since last July, I believe. It's been a good 8-9 months, and the committee is basically composed of myself, Abhishek. There's Layli, Fuhar, and Kar, who are from the same lab in the Chemical Engineering Department at UBC. There's Jaskaran from the University of Guelph, and he's a postdoctoral fellow there. And Feria is the one who helps update the website, and she's basically been the wheels behind this whole seminar series. It's also quite exciting for us to see the reach that WESTalks has had, and we've pretty much managed to reach every continent, I guess, apart from Antarctica, which is quite exciting. But the response from everybody has been overwhelming, and this also obviously does not include the views that we get on YouTube. So thank you so much for your support since we actually started this. All right, so today we have Dr. William Tarpeh from Stanford University, and we will be carrying on the WESTalks series right up till June 3rd, which will be followed by the West Conference. And we are also having some amazing speakers after this, so I'm hopeful that you guys will join us. Before I introduce the speaker today, I just wanted to point out that if you've missed out any previous talks, make sure you go to the IC Impacts YouTube page. I just checked Dr. Muhammad Ataya's video, and it has up to 370 views now, I think. So that's quite cool as well, that that's gaining a lot of traction on YouTube. And finally, today's speaker is Dr. William Tarpeh, and I'm quite excited to introduce him because I've read quite a few of his papers because I work in the same field. But Dr. William Tarpeh is an assistant professor of chemical engineering at Stanford University. The Tarpeh lab develops and evaluates selective separations in wastewaters at several synergistic scales, molecular mechanisms of chemical transport and transformation, novel unit processes that increase resource efficiency, and systems level assessments that identify optimization opportunities. Will completed his bachelor's in chemical engineering at Stanford, his master's and PhD in environmental engineering at UC Berkeley, and postdoctoral training at the University of Michigan in environmental engineering. Will has recently been honored as an environmental science and technology early career scientist, Forbes 30 under 30 2019 science list, which is quite an achievement, and the Gulf Research Program Early Career Fellowship, and also the Chemical and Engineering New Standard 12. So very excited to hear from you, Dr. Tarpeh. I'm going to hand it over to you now. And if you have any questions during the presentation, please make sure you put it in the chat, and we'll get to it towards the end.
Sounds great. Thank you very much, Abhishek. It's great to be here with you all. I particularly appreciate that we are on West Coast time as well. For those of us on the West Coast of North America, sometimes we have quite early calls, and that's okay. But I won't miss that when we go back to in-person things. But today I'm going to be talking about some of my lab's recent work on distributed nitrogen recovery from wastewater. I decided to start with this image because it really is an example of some of the thinking that we do in our lab, where we focus a lot on molecular mechanisms as a lab at the interface of chemical and environmental engineering. And we're always thinking about several scales up at the same time. So we're thinking about ways to control and design novel processes like electrochemical membrane reactors, and then also thinking about the really, really big picture in terms of what does the life cycle assessment, techno-economic assessment look like what would it look like if lots of people adopted the technologies we develop? And we love to interplay and go between these different scales, because we have seen over and over again that it leads to new and insightful discoveries that we find that we wouldn't necessarily find if we just looked at one of these circles. So today I'm going to focus on nitrogen recovery, a topic that's near and dear to my heart, but I'll show at least one slide of some of the other resource recovery cases, as we call them, that we work on in our lab beyond nitrogen. So starting with nitrogen, we work on nitrogen like many others because the nitrogen cycle has been drastically impacted by humans, and it's far overdue for a redesign for this century. So the natural nitrogen cycle, maybe unsurprisingly, nature is one of the best engineers I know. It's very well balanced in terms of inert nitrogen and all the other forms of nitrogen that we often call reactive nitrogen, ammonia, nitrate, N2O, NO, all these other forms that can interconvert. And this is well balanced between these two groups of these two groupings. Inert nitrogen is converted to reactive nitrogen by largely biological nitrogen fixation. And then reactive nitrogen is converted back into inert nitrogen by largely biological denitrification, also storage in soils and in biomass. Now, humans have drastically done two things to the nitrogen cycle. We have more than doubled its throughput. So now this anthropogenic nitrogen cycle is above 200 teragrams of nitrogen per year. And we've also skewed this cycle drastically to sources of reactive nitrogen rather than sinks of reactive nitrogen. And so in short, Haber-Bosch fertilizer production has far outpaced to the tune of two orders of magnitude wastewater treatment plant nutrient removal. So this leads to a net discharge of reactive nitrogen into both air and water. We'll focus on mainly water today. So in my group, we focus a lot on this green arrow. How do we interconvert different reactive nitrogen species to avoid going back and forth through nitrogen gas and just increasing the throughput and the associated emissions, nitrogen and otherwise, for the nitrogen cycle, the anthropogenic nitrogen cycle. Many of us in the water field are familiar with the consequences of our current nitrogen cycle. And so one of the biggest ones is harmful algal blooms. This is from the Gulf of Mexico in the southern US. It's a beautiful picture, but also a tragic picture because this green that you see is evidence of harmful algal blooms. And so these can lead to they result from overconsumption of oxygen due to over-fertilization by nutrients. And they can also produce cyanotoxins that are harmful to human health. And so when we think about wastewaters in general, most of the time, and it's very fair to say that wastewaters require investment of money, energy, and chemical inputs. The US Environmental Protection Agency spends about $270 billion every year on treating and transporting wastewater. In particular, this 40%, the red and orange here, are for secondary and tertiary wastewater treatment. In California, where I live, we spend about 20% of our state energy budget on treating and transporting water and wastewater. For those of us in the wastewater treatment space, we're familiar with several types of chemicals that we add to wastewater treatment plants. And these aren't bad, they're needed to be able to treat wastewater, but things like coagulants, flocculants, and also disinfectants. All of this to say, normally we think of wastewater, and we have for the past 100 years, as something that requires investment. Increasingly over the past few decades, our field has started to think about wastewaters as requiring investments, but also being potential sources for products. And so thinking about wastewaters as containing valuable chemical resources has been a term that has really changed some research trajectories in our field. So we kind of jokingly call this our food pyramid in our lab because it looks like a food pyramid, but more importantly, it's for recovering valuable products. And we like to think of how do we step up this pyramid to produce higher and higher value products, as in dollars per amount. And it's not to say that we shouldn't produce electricity, heat, and biofuels, these things that are the foundation and the bottom or base of the pyramid, but it's to say, what would the world look like if we could expand the product portfolio that we could generate from wastewater? It would allow us to have a diverse, robust portfolio that could allow us to tailor different products for different areas. And so we see our job as developing the unit processes to make this a reality. So as a second set of motivation, I wanted to also talk a little bit about global sanitation today and tie this back into our resource recovery work as well. So one of the biggest things about global sanitation is that our progress on sanitation infrastructure and treatment of excreta has been much slower than expected. So back in 2000, the United Nations got together and thought about the UN development goals. And these were the Millennium Development Goals. And these were the predecessors to the Sustainable Development Goals, the SDGs, which many of us are familiar with. And so in the MDGs, they divided sanitation into two categories, either improved or unimproved. Improved defined as separating humans from their excreta, unimproved defined as not doing so. And so an example of this unimproved is a hanging latrine, where you can see excreta could fall down easily into this water body where you see people, boats, etc. So humans are not separated from their excreta. So in a graphic version, the goal in 2000 was to have the number of people without access to improved sanitation, or with access to unimproved sanitation. So in 2000, the goal was to have this gray bar. Now, to kind of be fair and allow for the lag in reporting, it was to look at the 1990 level and use that. So we were supposed to take this 46% and have it 23%. And you can see we came shy of that, right? And this is accounting for population growth as well. And so we came close, but still shy of this by 2015. But the situation looks a lot worse when you think about not just separation of people from their excreta, but actual treatment of that collected excreta. And 2/3 of people don't have access to adequate treatment of their excreta. And so this really calls into question, especially this treatment calls into question the two major goals, arguable two major goals of sanitation, which are 1, to separate humans from excreta, and 2, to reduce environmental impact. So this first picture is a pit emptier, and this is a picture from Kenya. And the second picture at the bottom is about reducing environmental impact. So this is a picture from Ghana, and this excreta has been collected, but then it's being discharged, and arguably we're not necessarily reducing the environmental impacts of this waste that was collected. And so the big question that's been, I think if someone could answer this, we would be in a much better place, but we don't have great answers to this yet. But here are some of my thoughts based on my reading of the literature and my own experience. In terms of why is sanitation progress so slow? Some of the contributing factors are the fact that urban population growth is exploding. So this is an infographic showing sub-Saharan Africa from the UN Environmental Program. And if you look at all these different pie charts, the size has to do with the total population. But what I want you to focus on is the red portion. The red portion here is the share of the urban population that lives in informal settlements. And so informal settlements are defined not having adequate infrastructure, which includes wastewater treatment and sanitation. What we can see is that, especially in sub-Saharan Africa, the vast majority of these are specific cities in most of these countries, have the urban population growth is outpacing our ability to provide infrastructure. So that's one reason that sanitation progress is so slow. Another reason is the lack of market incentives. So in my own experience in several countries, we tend to have great ribbon cutting ceremonies when a new toilet or new ablution block is built. But then weeks, months, years later, toilets tend to fall into disrepair without adequate maintenance. And so there's a lack of incentives. There's not as much incentive to maintain a facility as there is to build a new one. And another contributing factor is our adherence to the centralized treatment model. So these are some data collated from a great paper by Tove Larsen from EAVAG and Max Maurer. And it's showing the percentage of people with access to sewered sanitation in Africa and Asia in 2010 and in 2050, assuming that we continue to depend largely on centralized treatment model. So what you'll see is that we'll fall woefully short. We continue with business as usual. So this calls for either accelerating the centralized treatment model or adapting to other methods and other modes of providing sanitation, like decentralized treatment. And so how we think about this and tie this back to our resource recovery is thinking about the fact that reimagining excreta can transform toilets from, just like wastewater, from not just things you invest money in, but things that actually generate revenue because they generate valuable products. So from a chemical engineering perspective, everything can be drawn as a unit process, aka a box. And so we think about toilets as a box where excreta goes in and waste comes out. But we could also think about recycling something of value from the waste stream to use on the excreta, such as a disinfectant, or in a separate commodity vertical, like fertilizer production. So all of this to say, these are two motivations in both centralized wastewater treatment and decentralized sanitation areas to think about how to design selective separations. And so for us, selective separations are our main tool to be able to realize the circular economy, but not just the general circular economy, but a very element-specific circular economy. So thinking about how do we make a nitrogen selective circular economy, or a phosphorus-specific circular economy, or a lithium-specific circular economy, and how do we do that across scales and across sectors, as shown in the kind of conceptual diagram. So when it comes to nitrogen, let's dig in and think a little bit about removal versus recovery. And we like to be really strict about these definitions in my group because it kind of changes how we think about the chemical and environmental engineering we do. So we define removal as conventional techniques tend to remove some pollutant from a stream that we care about. And after removal, there's if we get it out of the influent, then that's a success on a removal process. Now for a recovery process, it requires removal as a first step, but then an actual production of a value-added product as a second step. And so when it comes to wastewater nitrogen removal, we cycle nitrogen and wastewater to our wastewater treatment plants, and nitrogen, much of it present as ammonium, can be discharged and lead to these harmful algal blooms, eutrophication as seen here. Now, environmental engineers are familiar with nitrification, denitrification, a set of coupled biological processes that convert ammonium all the way to nitrate in the nitrification step, and then denitrify it to nitrogen gas. And so this is a great process. It's not something that I'm out to vilify or anything like that. It's just that if we zoom out of the control volume of wastewater nitrogen removal and include fertilizer production as well, we start to think about some other efficiencies that we could take advantage of. Namely, the fact that Haber-Bosch fertilizer production in some ways reverses nitrification, denitrification. It converts nitrogen gas into ammonium. And then we add that ammonium as fertilizer to crops and we get in this cycle. Now, this is not a bad cycle, but there are some efficiencies to take advantage of. First of all, nitrification, denitrification, and Haber-Bosch are both fairly energy intensive, chemically intensive, and costly processes, right? And second of all, what we're doing is investing all of those resources into using nitrogen gas as a kind of expensive intermediate. So we ask the question, why not recover the nitrogen while it's in the form that's useful? But to do that, we need to have selective separations and be able to pick out ammonium out of a very complex waste stream. So to do that, we use several different molecular properties that we can exploit. One is ionic radius. So in some of our adsorbent work, I'll talk about this graph in particular some more. We also think about acid-base equilibria. So taking advantage of the fact that ammonia can be protonated to ammonium, NH3 can be protonated to NH4+, and we can take advantage of pKa and its sensitivity to temperature. Solubility as well. So ammonia, for example, is a volatile species, so can be stripped from water solutions, thinking about Henry's constants. And then also intermolecular forces. So we'll get into a little bit of a linked exchange in addition to ion exchange, for example. So in our group, we sort of orient ourselves in this 2x2 matrix for most of the work we do. So one big pillar of the lab is selective materials, which I'll talk some about today. Another is our work on electrochemical processes. And then two other parts that are in some ways supporting and cross-cutting of both of the first two are contaminant fate. So we think about both organic contaminants and pathogens as well in terms of what's their fate in these new processes that we devise, and then also thinking about some of our work in resource-constrained communities. Great. So today I'll start with our work on adsorbance for resource recovery, and then I'll tell a little bit about some of our electrochemical work later. So when we think about adsorbance, we think about three criteria, and we emphasize the third, especially for recovery processes. The first is capacity. So most adsorbents are designed and they come with a manufacturer's guarantee of how many sites are available for a given. Selectivity is also important, especially for wastewaters. We do a lot of work in urine, and so we need to think about how many of those sites get occupied by ammonium versus sodium, potassium, or protons, for example. And then regenerability. And this is the one for a removal process. Regenerability is kind of a secondary characteristic. You're mainly interested in the lifetime of the resin and then how you can regenerate it so that you can then absorb more of your pollutant and remove it. For recovery processes, regenerability is in some ways the most important parameter, because that's actually when you make your product, right? So when you pass an acid over an ammonium-loaded resin, for example, that's when you make your product. And so high purity regeneration is actually really critical. So in some of our first studies, what we realized or came to appreciate, which is not necessarily surprising, is that selectivity depends both on the material that you design and the solution. And so we observed, in terms of absorption density and looking at several different adsorbents, we observed very high observed selectivity for ammonia. Most of the sites were taken up by ammonia. But the key here is that urine kind of gives you an advantage, right? Because nitrogen in urine is on the order of 5 or 6 times more concentrated in terms of ammonium concentration over potassium and sodium. So increasingly, we've started thinking more and more about intrinsic selectivity. So thinking about equimolar solutions, which are not realistic necessarily, but help us really dig down into the fundamentals of ammonium versus potassium selectivity, for example. Why are we focused in particular on ammonium and potassium? Coming back to this graph of hydrated ionic radius versus unhydrated ionic radius, we can see that ammonium and potassium are quite close in terms of their hydrated ionic radii. So close that physically they're hard to separate. So we wanted to go for one of the hardest separations we could achieve, knowing that if we wanted to separate ammonium from sodium, for example, we could also use physical pore screening, size screening. But we wanted to go for kind of the hardest here and say that if we can demonstrate ammonium versus potassium selectivity, then that gives us a good shot at ammonium versus other cation specificities. So first we started looking at intrinsic selectivity of basically every adsorbent that we could either get our hands on or make through a screen that we did for different hydrogels based on acrylamides. And we tried to look at intrinsic selectivity here as total ammonia nitrogen over potassium concentration or over adsorption. And what we saw here is that in order for an adsorbent to be identified as nitrogen selective, it should absorb more ammonia than potassium on an equimolar basis. And so what we did here is, and what we saw here was that not many of these adsorbents were actually intrinsically selective towards ammonia. And so even some of the ones that we made ourselves, these hydrogels, exhibited just a little bit, like we're talking 1.1, 1.2, really hard to see, but this drew us toward, hey, we need to think about some ways to make intrinsically selective nitrogen adsorbents. So one of my first PhD students, Brandon, who's in chemical engineering, and I started thinking about what if we could load transition metals onto these, onto some commercial resins. So we kind of went back to the drawing board after our first screen. And we thought, okay, let's start with commercial resins and think about low impact ways to modify them such that we can achieve ammonium selective adsorption. So what we landed on was the fact that if we can load transition metals like copper and zinc, for example, onto some conventional adsorbents like these weak acid carboxylic acid resins here, and once we load the transition metal, we can think about the adsorbate as ammonia NH3 instead of ammonium. If we do that, then what we're doing is kind of removing ammonium from the racetrack for selectivity between sodium, potassium, and ammonium ions, all of which are monovalent cations. And we're plucking ammonium off of that through a pH conversion and putting it on a separate racetrack where it's the only runner, right? And in that case, then that's how we achieve selectivity, right? Ammonia is interacting with these sites by ligand exchange, whereas sodium and potassium only have ion exchange available to them. And the sodium and potassium get outcompeted for these negatively charged sites by divalent metals. And so that allows us to achieve selective nitrogen adsorption. And then it's a matter of how do we get the ammonia off? We can protonate because we know that this ligand coordination chemistry isn't as strong for ammonium as NH4 plus as it is for ammonia NH3. So this was kind of the cycle that we imagined. So what this ends up looking like is that the ammonia concentration, there's kind of a sweet spot where it performs the way I just described. If the ammonia concentration is too low, then ammonia acts more like a weak base than a ligand. And what it does is strip off protons on the waters of hydration that are on this metal. And so we just get ammonium, but no sorption of ammonia to the metal ligand. And if the ammonia concentration is too high, ammonia will interact with the metal so much that you end up with a leaving group. That's a metal ammonia complex that simply goes in solution, making our separation sort of null and void. So this sweet spot that we thought about and ended up seeing in our data as well is that ammonia replaces just a few, and in fact 2 waters of hydration. And so the metal stays affixed to the to the resin, but can still absorb some ammonia as well. So what we saw here, and so those red and green areas are shown here on this graph as well. What we saw here was that we were able to achieve very high selectivity, so on the order of 6 or 10 here for TAN of K selectivity, as opposed to the 1 we saw earlier. And so this is a 2x2 matrix of copper and zinc as the metal, and 2 different parent resins. So the weak acid cation exchanger, which is a carboxylate, and then the sodium monodiacetate resin, the SIR resin. And so what we see here is we can achieve very high selectivity without sacrificing capacity. So for comparison, the capacity of these resins without the copper and zinc for ammonia is around 4 to 5 in these units, milliequivalents per gram of resin. And so we didn't sacrifice capacity, but we increased selectivity several fold. So then, as we tend to do, we moved on towards simulated and increasingly realistic solutions and saw that divalent ions can actually play a role here and can kind of disproportionately absorb because they can outcompete the metal, or they can compete more fairly with the metal that's needed for the ligand exchange. And so this type of approach would require pretreatment of divalents, which is not out of the scope for urine treatment in particular, because magnesium and calcium actually tend to settle out spontaneously if you just sit urine for any appreciable time. So to go back to this bar graph, what we saw here is that we observed very selective adsorbents with unprecedented selectivity over other adsorbents that we had seen for ammonia selectivity in particular. And so some of our ongoing work here has been characterizing not just the aqueous phase, but the solid phase as well, and looking at these differences in FTIR peaks to see that the regeneration restores the carboxylate stretch peak separation between these 2 dotted lines. So in short, the regenerated resin looks more like the copper-loaded resin than it does the ammonia-loaded resin. And so the other thing we've been doing is actually looking at selective regeneration and thinking about, most of the time when we talk about selectivity for adsorption, we think about the adsorption step. But what if we could also tune the regeneration to be able to increase the purity of our product? In short, even if sodium and potassium adsorb, what if we leave them on and get only the ammonia off to increase the purity of our product? And so we've been able to do that with just ionized water through some of the pH interactions that I won't jump into a ton of detail about now, but suffice it to say that for these adsorbed total ammonia nitrogen, we can get 60 or 70% off with just using DI water. And we can see the solution ratio of ammonium over potassium is very, very high. So this tells us we're going to get a high purity, or we do get a high purity ammonia solution. And so some of the ongoing things we're thinking about are urea as a solute, and also further benchmarking and alternative metal sources. Right now, we've been using virgin copper and zinc, but we can think about getting those from waste streams as well. So one of the Achilles heels of ion exchange and adsorption approaches is the regeneration step. And most of the time, it's seen as something where you just use concentrated acid, base, or brine just to quickly regenerate your adsorbent so that you can then get back to the business of doing removal. But again, in recovery, this becomes really important. So a study we did early on when I was still a PhD student was think about, let's imagine that every household in San Francisco, for example, had a urine diverting toilet and a cartridge that was a diversion that captured nitrogen and then let the rest of the urine go down the normal pipe to the wastewater treatment plant. And let's say people had those collected from their house every week. What would be the biggest impact categories for, or the biggest contributions to things like greenhouse gas emissions, energy, and total cost of this whole system? So before doing this analysis, our entire team would be transport, right? You basically need another fleet of garbage trucks to go to everyone's house every single day. Interestingly here, that transport is in white, this cartridge collection, and these are graphs of energy and greenhouse gas emissions by the number of facilities. And that white part is small, right? It doesn't vary, but it's small compared to the acid manufacturing for the generation. And so this kind of spurred a whole series of studies that were focused on how do we improve the use of sulfuric acid because it's so environmentally and energy intensive to produce. So the first thing we did was try to tune the concentration and the flow rate to try to use minimal amount of sulfuric acid. And that we met with some success. As further underlining the importance of this, in some of our work in Nairobi, Kenya, we saw that ion exchange was competitive with either just trucking urine away to a treatment plant And it was also competitive with fertilizers produced in Kenya in terms of the value per kilogram of nitrogen. But you can see within this bar, 2/3 of it is still the cost of the regenerant, not the cost of the resin, right? And so there's a lot of impetus here for reinventing how we do, or improving how we do regeneration of ion exchange resins. So just to take a quick ascent to our work in Kenya, through a study there, we determined that the real value of urine-derived fertilizers is that they're locally sourced because they don't experience imports like the vast majority of fertilizer in sub-Saharan Africa. And so just given that they're produced locally from raw materials locally, that allows us to basically have a little cushion in terms of the price we can charge and still be competitive is above the cost of producing the fertilizer. And the other thing we realized were that the key cost drivers were, again, regeneration and also supply chain. So this graph is showing toilet scale performance in terms of adsorption density over cycle for 10 cycles. Now, to carry on some of this work on regeneration, one of my postdocs, Lucas, has been focused on using electrochemistry to regenerate ion exchange adsorbents. So our first study on this, we used electrochemistry in a water splitting setup, so just a 2-chamber electrochemical cell to produce pH 11 and pH 3 solutions, and then use those to generate 2 ion exchange resins columns, one for phosphate and one for ammonium. And so what we saw is that just on the order of 30 minutes or so, we're able to produce this pH 3 and pH 11 solution. Now, this is not as extreme and maybe not as effective as using pH 1 and pH 14 solutions. But our argument here is that it's 1,000 times less intensive, right? We can do it on site. And let's say if we can get, see if we can still get a majority of sites regenerated. And in fact, we do. It's around 70% of the capacity. And this is repeatable over several cycles, more or less. And so this has been one thing that we've been looking at quite intensely. The next step we've been doing is actually integrating the ion exchange resin into some of these electric chambers specifically. So yeah, happy to take questions on that, but I'll leave it there for now. So to move on in terms of electrochemical nitrogen recovery, I want to dig into the last 10 or 15 minutes or so, dig into some of our work here as well on not just the material side, but on the process side as well. So one of kind of the founding cornerstones of our lab has been a process that we call electrochemical stripping. And the idea here is that it's like conventional ammonia stripping, but it simply uses electrochemical potential instead of a countercurrent exchanger. So for conventional stripping, a wastewater is fed in. You need a base to convert NH4 plus to NH3 so that it can volatilize out. And then you pass, you pump an air stream over the water so that the ammonia volatilizes out of the liquid solution and into the gas stream. Again, there's nothing wrong with conventional stripping. We're just looking for additional efficiencies that we might take advantage of. So for electrochemical stripping, the changes here, the novel parts, are that we can observe an in situ pH increase just by water electrolysis. So by splitting water, we can produce hydroxide ions, more or less. And so that can incentivize this technique for decentralized applications or remote applications. And then we can also observe internal ammonia stripping through a membrane rather than having to build a full counter current exchanger. So keep your eye on these chambers, this yellow, pink, and clear chamber. They're colored just for our purposes for today so that you can see the difference between them. So in electrochemical stripping, we recover nitrogen based on charge and also based on volatility. So here are the 3 chambers you just saw, anode, cathode, and trap chambers. So the anode chamber has a mixed metal oxide of titanium coated with iridium and potentially other metals in some of our experiments. And then in the cathode, we have a stainless steel electrode. So ammonia-rich wastewater is fed into the anode chamber. And at the anode, an oxidation reaction happens, and that provides electrons that go from the anode to the cathode chamber. That oxidation reaction tends to be the oxidation of water or the oxygen evolution reaction. And this acidifies the anode chamber and makes all of the ammonia present as NH4 plus. So as negative charges move, the electrons move through the external circuit. There's an impetus for positive charges to move as well due to the external potential that is established. And so we select for those using a cation exchange membrane. So that selects for things like sodium, ammonium, and potassium. So those make their way to the cathode. We've separated based on charge here. Now at the cathode, we can either reduce oxygen or reduce protons, both of which you can think of as an in situ pH increase. And so this is where we get the pH increase that deprotonates ammonium and turns it into ammonia. Ammonia is aqueous, but as I've mentioned, it's volatile. And so then we strip that ammonia out using more or less a membrane distillation in a polypropylene or polyethylene membrane that doesn't let liquid water through, but lets gases like ammonia gas through. And we reprotonate that in a trap chamber that has sulfuric acid in it. So we've separated nitrogen based on charge and based on volatility. And in short, it's one of, if not the only species that passes both of those tests in any wastewater. So our first proof of concept, we showed this graph is from real urine, and it's showing the mass of nitrogen versus time. And we can see the nitrogen leaves the anode chamber, goes to the cathode chamber, but ultimately ends up in the trap chamber. And so we did this for simulated solutions, synthetic urine, all the way up to real urine. We've since done it for several other real waste streams and shown that we can get around or above 90% recovery efficiency of nitrogen. And I'm not showing you the selectivity data because it's kind of it's a series of negative results to show that there's nothing else in the trap chamber, but happy to provide more details as needed. But the main key here is that electrochemical stripping is robust to work on several different waste streams, from reverse osmosis concentrate to real urine and anaerobic digester effluent. So with that in mind, we started digging over the past couple of years, we started digging into, okay, we have this process that is functional, it works, it achieves our treatment objective, but let's dig into either to modeling it better and understanding the comparative rates of different steps. And so one of my other first students, Matthew Liu, who's in chemical engineering, and I started thinking about prioritizing some of these operating parameters. So one, motivated by the graph I just showed you, was what's the influence of different ammonium concentrations, right, for different wastewaters or different dilutions thereof. And then we started looking predominantly at the gas permeable membrane, because in our first study, we had shown that this was most likely where the rate limiting step was occurring. But we looked at temperature here in particular to think about volatilization of aqueous ammonia to gaseous ammonia, and also the characteristics of this gas permeable membrane that I mentioned, its pore size, its tortuosity, things like this. So here we paired a model that we developed with our experimental measurements to characterize ECS, or electrochemical stripping performance. So in terms of experiments, we measured total ammonia nitrogen via ion chromatography in each chamber over time. And again, you'll see this removal recovery dichotomy coming up. Removal for us means getting it out of the anode, no matter where it goes, cathode or trap. Recovery, more specifically, means it has to get all the way to the trap, it being the ammonia. The ammonia has to make it all the way to the trap chamber. So the difference between removal and recovery is kind of what you leave on the table here in the cathode. And so from a modeling perspective, we sort of lumped all the mass transport and reaction steps that are happening in each chamber into one lumped mass transfer coefficient that we called HAC for the anode to cathode and HCT for the cathode to trap. So I'm just going to show the temperature results here for the sake of time. But for temperature, what we saw across the temperature range from 15 to 35 C, and we're looking at gamma here, which is recovery, we see that a higher catholyte temperature does increase recovery efficiency. So multiple ways to look at this. We can look at the end of the experiment and look at how the recovery is higher at higher and higher temperature. We can also look for a given recovery efficiency and draw a horizontal line and say, okay, how long did it take us to reach that? And in this case, it took 2 hours longer to reach around 50% recovery efficiency in the cold case versus the hot case. Now, interestingly, higher catholyte temperature does not appreciably affect removal efficiency. These points with their error bars all sort of collapse onto each other. And so this again is not too surprising, but allows us to really model and understand what's happening. And from the modeling perspective, we could look at this as our lumped mass transfer coefficients, HAC, which aligns with removal, and HCT, which aligns with recovery. And we can look at those in terms of temperature. And what we see here is that HAC, the removal paired parameter, doesn't really increase much with temperature, but HCT more than doubles. And so this again pointed to the fact that this and other experiments showed that volatilization, in fact, was the key rate limiting step and pushed us into further engineering of these processes to think further. So beyond electrochemical stripping, we aimed to do two things: expand the product and pollutant portfolios for nitrogen recovery. So electrochemical stripping can expand or can recover acidic ammonium recovery, like ammonium sulfate, for example. But for products, we wanted to think about, what if we wanted to produce alkaline ammonia, something like ammonia hydroxide that can be used as a disinfectant or a chemical precursor. And then we could also think about other pollutants. I've talked almost exclusively about ammonia as the influent pollutant, but what if we could produce ammonia from nitrate? So I'll just focus on the left-hand side of this as I finish up today, but happy to talk more about nitrate reduction and how we're producing ammonia from nitrate in wastewaters as well. So one of my students, Anna, who's in civil and environmental engineering, has been thinking a lot about expanding the product portfolio through something we call flexible electrochemical stripping. So this is another version of ECS that you've seen in this talk already. In flexible electrochemical stripping, we add a chamber and add a circuit that allows us to recover and tune the production of ammonium sulfate fertilizer in an acidic form or ammonium hydroxide in an alkaline form. And so one of the last results slide I'll show you today is looking at the performance of FvCS, flexible electrochemical stripping, in high strength wastewater. And this is collected from some of our partners in Senegal. So this is fecal sludge, concentrated wastewater, more or less. And so what we see here is these are different efficiencies all out of 100% versus time. And we see complete removal within 1 hour. But the thing I really want to focus on here is the recovery of either ammonium sulfate or ammonium hydroxide. And you can see that just by controlling the time here, we can control the proportion of those two different products. So you can imagine storing up this acid and then being ready to convert it to base on demand. Now, we could also do this by staggering when we turn on the second cell. And so we could produce completely ammonium sulfate to start with, and then literally on demand start producing ammonium hydroxide here and still observe high recovery efficiency. So this work is still ongoing, but I wanted to end just with one last study that we've done, this sort of big picture thinking about designing the future of distributed nitrogen recovery. And we've thought a lot about how to integrate academic and industrial priorities. So this is a new study that just came out a couple of months ago in ACS, ES&T engineering. And so this Sankey diagram is showing kind of all the different relationships between mechanisms, nutrients, nitrogen, phosphorus, or both, and objective. And one of the things that pops out at me from this, this diagram is the fact that most nitrogen processes reported in literature are focused on removal, not necessarily recovery. And so this is not a bad thing, but it's a thing to think about when we're thinking about nitrogen recovery and how to contextualize it in terms of all the work that's going on academically. Another chart I'll just plug here briefly is we looked at integrating and kind of the mismatch that occurs between practitioners, how practitioners value different metrics, and how academics value different metrics in terms of how we report them in literature. And so if these were aligned, you would see all of them in quadrants 1 and 3 here. But interestingly, and maybe this isn't too surprising, some of the things we see that are kind of out of alignment here are things like cost. Practitioners want to hear more about cost. Academics, we're not reporting cost, right? And so this is pushing us to think about but from a systematic review of over 157 different technologies, is thinking about what are the big insights we can gather from the literature and think about how to actually accelerate nutrient recovery and not have it take decades like most wastewater innovations do. So with that, just wanted to quickly summarize what we're doing in my lab. I focus mainly on selective materials and electrochemical processes today. I promise one slide, not just on nitrogen, just to give you a quick thought about some of the other things we do in terms of desalination, brine, valorizing sulfur, and we've just started a project on lithium recovery. Definitely want to thank my many collaborators and the students and postdocs in my group, and I'm happy to take your questions as you have them.